In the year 1974, we directed a radio telescope towards the star cluster M13 and broadcasted humanity's inaugural deliberate communication to extraterrestrials. The gesture was largely symbolic. M13 is situated 25,000 light-years from us. What we had not foreseen, however, were the nearer neighbors who could have already been monitoring our unintentional transmissions. In fact, for 123 years, humanity has been addressing the universe without authorization. Every broadcast of a baseball game, every sitcom signal, every radar ping directed at a planet has been leaking out into space, forming a growing sphere of human communication. Subsequently, beginning in 2017, enigmatic interstellar bodies started to pass through our solar system with growing regularity. Oumuamua, Borisov, and now 3I Atlas, each one more peculiar than the one before. What if our century of electromagnetic emissions finally found a listener? What if these are not naturally occurring events, but the universe's response, confirming our message was received? Remain with me until the conclusion to learn how our cosmic dialogues might at last be receiving replies. Now, brace yourselves. We commence Part 1, Shouting into the Dark. For more than a century, humankind has been communicating with the cosmos, not intentionally per se, but communicating all the same. Every AM radio station sending out baseball games into the darkness, every television antenna beaming sitcoms toward the sky, every planetary radar signal we launched at Venus or a stray asteroid. All of this has been seeping into space at the velocity of light, generating an expanding sphere of human conversation that currently reaches approximately 130 light-years from Earth. We refer to this as our radio bubble, a sphere of electromagnetic activity that declares our existence to any potential listeners. Yet there are two categories of signals we have sent into the void. The first are unintentional, radio leakage. The accidental spillover from a civilization that mastered the manipulation of the spectrum before we understood the importance of discretion. The second category comprises purposeful messages in bottles cast into an ocean we can hardly comprehend. In 1972 and 1973, we dispatched Pioneer 10 and 11, bearing golden plaques that illustrated naked humans and indicated our position within the galaxy. This was an optimistic, maybe naive act. The plaques depicted the hydrogen atom's spin-flip transition, offering a universal standard for time and distance. They charted our solar system and identified Earth as the third planet orbiting a medium-sized star. Most audaciously, they featured images of a man and a woman standing next to the spacecraft for scale, their hands raised in what we intended as a universal gesture of welcome. The Voyager Golden Records came next in 1977, representing a more ambitious endeavor. Chuck Berry's Johnny B. Good now spins through interstellar space, accompanied by whale songs and salutations in 55 languages. The records held 116 images, displaying the variety of life and culture on Earth, along with mathematical and physical definitions, the solar system, DNA structure, human anatomy, conception and birth, family units, architecture, art, and music. Carl Sagan described it as a message to the universe. Others termed it cosmic graffiti. But the most concentrated shout originated from Arecibo in 1974. Frank Drake and his colleagues pointed the enormous dish at the globular cluster M13 and transmitted precisely 1,679 bits of data. Why 1,679? Because it is the product of two prime numbers, 23 times 73. Any entity receiving it would notice this mathematical clue and arrange the bits into a rectangular pattern. The message would then appear as a pixelated image showing our numeral system, the structure of DNA, a basic human form, and our solar system with Earth highlighted. The broadcast lasted exactly 3 minutes and consumed nearly 1 million watts of energy. For those short moments, Arecibo was the most luminous radio source in our immediate galactic vicinity. The signal sped towards M13 at the velocity of light, bearing humanity's first intentional effort at interstellar communication. It was truly a ceremonial act. M13 is 25,000 light-years distant. By the time our communication arrives, human civilization will have experienced several cycles of rise and fall. Still, we sent it, because occasionally the act of reaching out is more significant than the hope of a reply. Giuseppe Cocconi and Philip Morrison had already laid out the logic for us in 1959. In a publication in Nature, they contended that radio waves would serve as the universal medium for interstellar dialogue. They indicated the water hole, that tranquil section of the spectrum between 1,420 and 1,666 gigahertz, defined by the emission lines of hydrogen and the hydroxyl radical, OH, the fundamental components of water. Any civilization with an understanding of chemistry would know to search there. The hydrogen line at 1,420.4 megahertz grew especially important. This frequency corresponds to the energy differential when a hydrogen atom's electron changes its spin from parallel to antiparallel alignment with the proton's magnetic field. It is the most plentiful element in the universe undergoing its most basic transition. If aliens wish to create a universal communication standard, hydrogen's signature would be the clear selection. Our own searches have adhered to this line of reasoning for decades. The SETI Institute's receivers scan the hydrogen line. Breakthrough. Listen monitors millions of stars over various frequencies. The logic holds true. If you wish to be heard across interstellar voids, you broadcast where the galaxy is naturally silent. But here is what we have discovered about our own transmissions. They are surprisingly difficult to detect. The majority of our television and radio signals, once they pass through Earth's atmosphere, become indistinguishable from cosmic background noise within just a few light years. The inverse square law is relentless. If you double the distance, the signal's power reduces to 1/4. Only our most powerful broadcasts can survive the trip to nearby stars. Planetary radar systems like Arecibo's S-band transmitter or Goldstone's X-band array are bright enough to be detected across interstellar distances. These systems, created to map asteroids and planets, unintentionally act as cosmic lighthouses. Their beams scan across the cosmos with each rotation of the Earth, generating a unique signature that would be unmistakable to any civilization observing our sector of space. The Deep Space Network is humanity's most advanced effort at creating a cosmic communication infrastructure. 3 huge antenna complexes located in California's Mojave Desert, near Madrid, Spain, and outside Canberra, Australia, provide uninterrupted contact with our robotic probes distributed across the solar system. These dishes, some as wide as 70 meters, could be perceived by an alien radio telescope from the edge of the known universe. To an alien observer, our spectrum would appear distinctive. Narrow carrier signals would materialize and vanish as our planet spins. The organized emissions of FM radio and television would be visible, with each channel occupying its assigned frequency band. Short, powerful radar pulses would sweep across the sky in predictable patterns. All of this activity would be concentrated around a small blue planet that seems exceptionally busy in the radio frequencies. The International Telecommunication Union safeguards specific frequencies for radio astronomy, acknowledging that some bands must be kept free for us to listen to the universe. Radio quiet zones established around major observatories limit terrestrial broadcasts that could disrupt sensitive receivers. The National Radio Quiet Zone in West Virginia covers 13,000 square miles, forming an area of electromagnetic tranquility around the Green Bank Observatory. The United Nations Office for Outer Space Affairs manages international space policy, although it has never had to handle incoming correspondence from space. Its charter is focused on the peaceful utilization of outer space. However, these frameworks presuppose human entities acting within terrestrial legal frameworks. No one has given serious thought to how international law would be applied to visitors from other star systems. This leads us to a core conflict within the SETI community. Conventional SETI has always centered on listening or passive reception. Breakthrough Listen analyzes petabytes of information from radio telescopes globally, seeking patterns that seem out of place. The SETI Institute runs the Allen Telescope Array in Northern California, where 42 dishes collaborate to scan the stars for artificial signals. However, there is another faction, known as Active SETI, or sometimes METI, Messaging Extraterrestrial Intelligence. These scientists advocate for transmitting powerful, deliberate messages into space. They maintain that if everyone is only listening, then no one will ever receive anything. The galaxy could be teeming with civilizations, all passively waiting for another to initiate contact. Their ideas bring up challenging issues. Export control laws classify high-power transmitters as potential weapons. Radio systems with the capacity for interstellar communication could, in theory, be adapted for military use. And then there is the more profound philosophical dilemma. Who authorized us to represent Earth? Should such critical choices be made by small circles of scientists and engineers? The history of false positives makes everyone wary. In 1967, Jocelyn Bell Burnell found an astonishingly regular radio signal from space. A pulse occurred every 1.337 seconds, as precise as an atomic clock. The Cambridge team briefly entertained the idea of alien intelligence. They even designated it LGM-1 for Little Green Men 1. The Discovery team considered whether they were observing proof of a galactic civilization. It was later identified as the first known pulsar, a rotating neutron star whose radio beam swept past Earth like that of a lighthouse. The precision was not a product of artificial intelligence. It was physics operating at extremes that pushed matter to its absolute limits. Neutron stars contain more mass than the Sun within a sphere just 20 kilometers in diameter. Their magnetic fields are trillions of times more potent than Earth's. When such celestial bodies rotate quickly, they become cosmic beacons of remarkable regularity. Then we have the renowned WOW signal, picked up by the Big Ear Radio Observatory in 1977. For 72 seconds, the telescope registered an exceptionally powerful narrowband broadcast near the hydrogen line. The signal was so remarkable that astronomer Jerry Amon inscribed "Wow" in the margins of the computer printout. The transmission exhibited traits that SETI researchers had long anticipated for artificial signals: narrow bandwidth, high intensity, and a frequency aligned with hydrogen's natural emission line. Despite decades of subsequent observations, we have never been able to detect it again. Hypotheses are plentiful. It could have been a singular transmission from an alien civilization, a reflection of an Earth-based signal off space debris, or some yet unknown natural event. The signal continues to be one of SETI's most profound mysteries, but it also serves as a cautionary reminder of the difficulties in differentiating artificial signals from cosmic background noise. These events have taught us important lessons. Extraordinary assertions demand extraordinary proof. Any potential signal must be repeatable, detectable by several observatories, and confirmed as being of extraterrestrial origin. The field has established strict protocols for verification and public announcement, aimed at preventing false alarms from causing worldwide panic or eroding scientific credibility. The Rio scale, analogous to the Richter scale for earthquakes, offers a system for assessing the importance of potential SETI discoveries. Ratings from 0 to 10 take into account both the signal's apparent artificiality and its potential effect on human civilization. The majority of candidates receive scores between 1 and 3, indicating they are interesting but not definitive. A confirmed signal from an advanced alien civilization would be rated an 8 or 9, signifying one of the most momentous discoveries in human history. Popular culture has also influenced our expectations. From Orson Welles' War of the Worlds, broadcast in 1938, to contemporary films like Contact and Arrival, We have been simulating first contact scenarios for generations. These narratives affect how we perceive the search, fostering both hopes and anxieties that may not align with the actual situation. Science fiction frequently depicts alien contact as a dramatic and sudden event, with massive spacecraft appearing in Earth's skies or powerful signals that instantly transform human society. However, real SETI concentrates on more subtle possibilities, such as faint signals from distant civilizations, archaeological signs of ancient visitors, or technological artifacts adrift in interstellar space. But here is the issue with shouting into the darkness. After a while, you begin to question if anyone is listening. We have been broadcasting for over a century now. Our radio bubble is still expanding, taking the sounds of human civilization to nearby stars. Each year, our electromagnetic footprint reaches new solar systems, signaling our presence to potential observers. If someone out there has been paying attention, if they picked up our first television broadcasts, our radar pulses, our deliberate messages, they would have had decades to formulate a response. The physics are simple. Signals move at the speed of light. Therefore, replies from nearby stars would be received within decades of our original transmissions. The question that keeps SETI scientists up at night is not whether intelligent life exists in the universe. Statistical arguments imply that the galaxy should be abundant with civilizations. The question is more straightforward and, in a way, more unsettling. What if someone finally answered? Part 2. The first answer night and the birth of 3 Atlas. On the 1st of July, 2025. The Atlas telescope at Rio Hurtado, Chile, was performing its primary function, surveying the southern sky for any object moving too quickly or shining too brightly. The asteroid terrestrial impact. Last Alert System manages 4 robotic observatories, their cameras capturing images throughout the night, compiling a registry of every rock that could pose a threat to Earth. Atlas is at the forefront of automated celestial surveillance. Each observatory takes pictures every 30 seconds, covering vast areas of the sky with each shot. Advanced algorithms analyze successive images, identifying objects that shift against the background of stars or exhibit unusual changes in brightness. The system was developed to find potentially dangerous asteroids weeks or months before they could strike, providing humanity with time to counter cosmic dangers. At 3:42 UTC, the automated detection system of Atlas IV identified something peculiar in the constellation Microscopium. It was a point of light moving against the stellar backdrop at nearly 3 arcseconds per hour. This was fast, quicker than any asteroid should be traveling at that distance. The object was already within Jupiter's orbit and approaching the inner solar system. The detection algorithms immediately started to compute its initial orbital characteristics. The object's position and speed pointed to a path unlike any recorded in the asteroid catalogs. Preliminary calculations suggested an eccentricity exceeding 1, the mathematical indicator of an unbound trajectory. This was not gravitationally captured material from the asteroid belt. This was an object from interstellar space. Within 6 hours, Pan-STARRS in Hawaii and the Zwicky Transient Facility in California provided confirmation. The object was genuine, it was swift, and its trajectory was impossible for any natural inhabitant of our solar system. 3 separate observatory systems had spotted the same anomalous object, ruling out the chance of equipment malfunction or cosmic ray interference with the detectors. The Minor Planet Center in Cambridge, Massachusetts, acts as the global hub for discoveries of asteroids and comets. Their computers processed the object's orbital elements and reached a disquieting conclusion. It had an eccentricity of 1.47, signifying a hyperbolic excess velocity of about 15 kilometers per second. This object was not gravitationally tied to our Sun. It was an interstellar traveler on a hyperbolic path that would take it through our solar system and then back into the galaxy. This discovery prompted immediate follow-up observations from major observatories around the world. The European Southern Observatory's Very Large Telescope in Chile started to track the object with four 8.2-meter mirrors operating together. The Keck Observatory in Hawaii also participated, employing adaptive optics to obtain diffraction-limited images. The Hubble Space Telescope was given emergency observation time to study this uncommon interstellar visitor. A designation was assigned swiftly: 3I Atlas. The 3I signified it was the third confirmed interstellar object after 1I Oumuamua in 2017 and 2A Borisov in 2019. The Atlas suffix was to honor the observatory that made the discovery, in line with the tradition of giving credit to the first to detect significant astronomical bodies. However, 3I was distinct from its forerunners. It was larger, brighter, and moved in a manner that did not entirely align with conventional physics. Oumuamua had been a tumbling, elongated rock about the size of a city block. Its light curve indicated an extreme shape, with a length at least 5 times its width, and possibly much greater. The object's reflection of sunlight was strange, exhibiting characteristics unlike any known asteroid or comet. Most perplexingly, it displayed signs of non-gravitational acceleration, small propulsions that could not be accounted for by the sun's gravity alone. Marco Micheli's team at the European Space Agency had meticulously examined Oumuamua's trajectory, utilizing data from the Hubble Space Telescope and ground-based observatories. Their 2018 paper in Nature detailed systematic deviations from purely gravitational movement. The accelerations were minor but statistically noteworthy, around 5 times 10 to the -6th meters per second squared, approximately 10,000 times less than Earth's surface gravity, yet undeniably real. Some scientists hypothesized outgassing, similar to a comet but without a visible tail. The accelerations could have been caused by sublimating ice, creating minute rocket-like effects as the object warmed up near the sun. Others put forward more unconventional theories, such as a piece of an alien light sail being pushed by stellar radiation pressure, or fragments from a disrupted comet with an unusual composition. 2I Borisov acted more predictably. It was a standard comet from interstellar space, featuring a fuzzy coma and a clear tail that was visible to ground-based telescopes. It adhered to the physics textbooks perfectly, which was a relief to astronomers, suggesting that most interstellar objects would be natural, albeit infrequent. Borisov's composition was very similar to that of comets in our solar system, with water ice, carbon monoxide, and organic compounds sublimating as it neared the sun. 3 Atlas was somewhere between these two extremes, and that is what made it so scientifically captivating and potentially alarming. Initial photometry showed a light curve that was unlike anything in the records. Most asteroids tumble in a chaotic manner, their brightness fluctuating as different surfaces reflect the sunlight. This tumbling is a result of their collision history, impacts that set them spinning in complex rotational states. However, 3I exhibited quasi-periodic modulation, regular fluctuations that indicated it was rotating in a controlled, almost mechanical fashion. The light curve displayed primary variations with a period of roughly 7.3 hours. Yet, within that cycle, there were secondary oscillations that hinted at a complex shape or surface features. Most fascinatingly, the periods remained remarkably stable over weeks of observation. Natural tumblers usually show variations in their period as their rotational states change due to various torques, but 3I kept a consistent timing, as if something were controlling the object's orientation. Spectroscopic observations from the European Southern Observatory brought more enigmas to light. The object displayed subdued signs of outgassing even though it passed close to the sun. Most comets show distinct spectral characteristics, with emission lines from sublimating water, carbon monoxide, and other volatile substances. However, 3I's spectrum was exceptionally clean, mainly consisting of reflected sunlight with only faint hints of gas emissions. The reflectance spectrum did not correspond to any known type of asteroid or comet. The colors were off, being too red for typical silicate materials and too rich in organic compounds. Absorption features suggested the presence of surface materials that could be rare or artificially created. Some spectroscopists proposed exotic carbon compounds or even metallic films as possible explanations for such unusual optical properties. Radio astronomers at Goldstone attempted to probe the object using their planetary radar system. The 70-meter Deep Space Network antenna broadcast powerful pulses at 8.56 GHz, the same frequency employed to map Venus and monitor near-Earth asteroids. The returning signal was faint but captivating. Instead of the rough, scattered echo typical of an asteroid's uneven surface, 3I Atlas produced specular reflections, flat, mirror-like returns that indicated smooth surfaces oriented at precise angles. The radar cross-section was smaller than anticipated for an object of its optical brightness, suggesting either an unusual composition or a geometry that dispersed radio waves in unforeseen ways. When the James Webb Space Telescope directed its infrared vision towards 3I Atlas, the data became even more peculiar. The JWST's extraordinary sensitivity uncovered thermal characteristics that were difficult to explain simply. The object's thermal signature pointed to a low albedo, meaning it absorbed most of the sunlight that struck it, as one would expect from a dark, possibly organic-rich surface. However, within that thermal emission were high-intensity specular spikes, narrow beams of reflected infrared radiation that materialized and vanished as the object rotated. This pattern was in line with thin film structures or engineered coatings that could reflect light at certain wavelengths while absorbing others. Natural materials seldom exhibit such selective optical traits. Ground-based observatories in Chile synchronized their observations, leveraging the Southern Hemisphere's superior viewing conditions. The object was set to remain visible until December 2025, providing astronomers with a valuable opportunity to examine humanity's third interstellar visitor. The Atacama Large Millimeter Submillimeter Array also participated in the effort, looking for molecular emissions that could shed light on the object's composition and internal structure. The discovery sparked considerable scientific interest, but was communicated to the public with great care. Space agencies had taken lessons from the Oumuamua incident, where speculative theories about alien technology had filled the news before a thorough scientific analysis could be completed. Official statements highlighted the object's interstellar origins and unusual characteristics, while steering clear of premature speculation about its artificial nature. However, it was the radio observations that shifted scientific curiosity into a state approaching apprehension. On the 15th of July, 2 weeks after the initial discovery, radio telescopes at various locations picked up a faint, narrowband carrier signal that seemed to be moving in tandem with 3I Atlas. The frequency was approximately 1,420.4 MHz, just a slight deviation from the hydrogen line, the universe's most significant radio frequency and the customary focus of SETI searches. The signal was detected simultaneously by the Very Large Array in New Mexico, the Green Bank Telescope in West Virginia, and FAST in China. Independent observations from different continents ruled out the possibility of local interference or equipment malfunctions. The signal was authentic. It was of extraterrestrial origin, and it appeared to be coming from humanity's third interstellar visitor. Radio frequency interference is the primary challenge for radio astronomy. Transmissions from satellites, cell towers, and even microwave ovens can taint observations with spurious signals that resemble astronomical phenomena. However, this signal successfully passed every test for extraterrestrial origin. It was only present when antennas were aimed at 3I Atlas. It exhibited a Doppler shift that perfectly matched the object's motion. Its intensity and frequency characteristics remained consistent over multiple observation periods. Initially, the signal showed no apparent modulation, just a clear, narrowband tone that drifted in frequency as 3I Atlas traveled through space. The Doppler shift confirmed that the source was moving with the object, not stationary in the background sky. The frequency stability was remarkable, indicating a highly advanced oscillator synchronized with atomic frequency standards. The initial response from the scientific community was one of cautious disbelief. Extraordinary claims require extraordinary evidence. Natural phenomena can sometimes generate narrowband radio emissions, such as from pulsars, masers, or plasma interactions in planetary magnetospheres. But the frequency was suspect. Why broadcast so near the hydrogen line unless the intention was to be heard by astronomers who knew where to search? Yet, as confirmations arrived from observatories across the globe, an unsettling possibility started to take shape. 3I Atlas was transmitting deliberately. The media naturally showed no such caution. Despite careful classification by government bodies, information about the radio detection was leaked within hours. Social media platforms were flooded with speculation. The hashtag #ThasherTheReply began to trend on Twitter. YouTube videos with titles like "Proof, Aliens Answer Our Call" amassed millions of views. The object that astronomers referred to as 3I Atlas was given a variety of unofficial names: the Messenger, the Reply, Visitor 1. Amateur radio enthusiasts worldwide started to monitor the hydrogen line frequency, hoping to catch the signal themselves. Software-defined radio systems, which are affordable and widely accessible, enabled thousands of individuals to join in the observations. The open nature of radio astronomy meant that the discovery could not be concealed or controlled by official bodies. Scientists attempted to keep things in perspective. The signal might be natural, a result of some unknown plasma phenomenon, or a unique interaction between the object and the solar wind. Radio emissions from comets were not unheard of, though they usually happened at different frequencies and had different characteristics. The proximity to the hydrogen line frequency could be a coincidence rather than a deliberate choice. Government space agencies released cautious statements, stressing the preliminary nature of the findings. NASA's press releases focused on the facts: trajectory, size estimates, orbital evolution, and radio detection. They steered clear of speculating about artificial origins, although internal communications suggested a different story. In private, planetary defense coordinators were posing difficult questions about objects that could maneuver and communicate. The Planetary Defense Coordination Office, which was set up after the meteor impact over Chelyabinsk in 2013, had been centered on natural dangers like asteroids and comets that could collide with Earth. But 3I Atlas introduced a new kind of risk. How do you evaluate the threat posed by an object that might be under intelligent guidance? The name 3I Atlas remained in use in official circles, but the public's imagination was captured by more descriptive titles. The Reply resonated with a key aspect of humanity's collective psyche. We had been sending signals into the void for more than a century: radio waves, television broadcasts, and deliberate messages like the Arecibo transmission. Now, it seemed, someone had finally responded. The premise of what was to come was both straightforward and profound. For the first time in human history, we would consider the idea that an interstellar visitor was not just a cosmic chance event, but a response to our own transmissions into space. Every observation, every measurement, every analysis would be carried out with strict scientific rigor, yet all would be shaped by a single question. What if 3I Atlas heard our call and chose to reply? The consequences, if this were true, would revolutionize every belief we hold about our position in the universe. We were not alone. Someone was out there listening, and they had journeyed across the galaxy to inform us that they had detected our voice among the stars. But first, we needed to establish whether we were facing an extraordinary natural event or something entirely different. something that had traversed the interstellar expanse with the specific purpose of finding us, bringing a message we were just starting to comprehend. Part 3. A wave of visitors, not a one-off. 3 Atlas was not an isolated case. 3 weeks following the initial finding, automated sky surveys started to identify more fast-moving objects with hyperbolic trajectories. The pattern of detection indicated an event unprecedented in the annals of astronomy. Multiple interstellar visitors arriving within a few months of one another. Their appearance seemed coordinated in a way that defied all assumptions about random cosmic occurrences. 4. I was identified in the data from the Catalina Sky Survey on the 22nd of July, 2025. The Lincoln Near-Earth Asteroid Research Program spotted 5I 2 days after that. By August, amateur astronomers using their own backyard telescopes were adding to an expanding list of interstellar visitors. Their findings were confirmed by professional observatories employing telescopes that had cost hundreds of millions of dollars. These were not random pieces of cosmic debris thrown out by some distant stellar event. The objects had common traits that grew more alarming with each new discovery. Firstly, their approach paths. A statistical analysis of interstellar object trajectories should reveal a random distribution, with objects coming from all directions as they move through the galaxy's gravitational field. However, this group displayed a loose coordination that went against expectations by several orders of magnitude. Their paths converged from a section of the sky about 15 degrees wide, centered on the constellation Lyra, as if they had all been sent from the same general area of space. Dr. Alan Fitzsimmons at Queen's University Belfast was in charge of the statistical analysis. His team determined that the likelihood of such coordination happening by chance was roughly 1 in 50 million, far below the level required to claim statistical significance in any other area of astronomy. Something had directed these objects towards our solar system with a precision that suggested intelligence and sophisticated technology. Even more concerning, their perihelia, their closest points of approach to the Sun, were all within a narrow band of distances, between 0.8 and 1.2 astronomical units. They were navigating through the very region of Earth's orbit, passing through the area where our planet journeys around the Sun. The accuracy of their targeting was exceptional, hinting at a knowledge of our solar system's layout and possibly Earth's exact position. The probability of natural interstellar objects coincidentally converging on Earth's orbital zone was extremely low. These visitors had been sent towards us. Their trajectories were calculated to provide the best observation opportunities from Earth-based telescopes while keeping a safe distance from our planet. Analysis of their light curves revealed more patterns that were difficult to explain naturally. While 3I Atlas seemed to be a thin, rotating panel with a controlled orientation, the later objects displayed even more unusual shapes. The brightness fluctuations of 4I indicated a needle-like form with an aspect ratio close to 20:1, which is longer and thinner than any known natural object in the solar system. The photometric data showed that 4I was tumbling end over end with a period of about 3.2 hours. However, this tumbling was not chaotic, like that of a natural collision fragment. The rotation exhibited signs of controlled movement, as if internal systems were adjusting the object's orientation for optimal solar energy absorption or communication purposes. 5I appeared to be a tumbling fragment, its light curve displaying complex variations that suggested a partially broken structure. Spectroscopic analysis uncovered unusual surface characteristics with materials that could be porous or partly hollow, leading to optical properties unlike those of any known asteroid or comet. A smaller object, designated 6I, had light curves that were consistent with what astronomers could only describe as a flake, something thin and pliable that seemed to ripple as it moved through space. The changes in brightness suggested a sheet-like structure that might be warping due to thermal stress or actively altering its shape. These forms were at odds with conventional asteroid physics. Natural fragments from collisions adhere to predictable patterns based on material strength and impact forces. Rocky bodies usually break into roughly spherical pieces. Icy comets split along structural weaknesses. However, thin film structures like sails, sheets, or panels would behave exactly as the observations indicated. The implications were deeply unsettling. Natural processes do not typically create objects with such extreme aspect ratios and controlled rotational states. Yet artificial structures designed for interstellar travel might exhibit precisely these features, especially if they were engineered for minimal mass and maximum surface area. Radio telescopes across the globe synchronized their observations, monitoring each object as it neared perihelion. The findings presented a picture that questioned every assumption about interstellar visitors. Each object was emitting narrowband radio signals near the hydrogen line, but these signals were not all the same. They had different modulation patterns, different frequency offsets, and different timing characteristics. The radio signatures pointed to a distributed communication network rather than just coincidental emissions. 3i Atlas continued its steady carrier tone at 1,420.4 MHz. 4i broadcast at 1,420.6 MHz with subtle changes in amplitude. 5i sent out short bursts at various frequencies within the waterhole spectrum. 6i generated complex signals that appeared to contain encoded information in both their frequency and timing. The variety of these signals made simple explanations based on natural phenomena unlikely. Plasma interactions, or masers, would exhibit similar characteristics in objects with similar compositions and trajectories. However, these visitors were broadcasting as if they were part of a coordinated fleet, with each one contributing to a larger communication effort. Dr. Elena Vasquez at the Arecibo Observatory put forward what came to be known as the staging hypothesis. The objects were not arriving randomly, nor were they debris from a single catastrophic event. They were part of a carefully planned sequence designed to maximize visibility and redundancy, while reducing the chance that their message would be overlooked or ignored. The staging strategy was logical from an engineering standpoint. If you aim to communicate with a newly discovered technological civilization, sending multiple messengers would increase the likelihood of success, even if some were missed or misinterpreted. The diverse characteristics of each object offered different kinds of proof for their artificial origins, making it progressively harder to write off the entire group as natural occurrences. The timing of their arrivals was also highly suggestive. When astronomers calculated the launch windows needed for each object to arrive at its observed time, assuming interstellar travel speeds of 10 to 20% of the speed of light, they discovered links to Earth's broadcast history that seemed too precise to be mere coincidence. 3i Atlas, if sent from a star system about 50 light-years away, would have started its journey around 1975, the era of powerful television transmitters and the first major planetary radar campaigns. The timeline for 4i corresponded with the early space age and the building of large military radar facilities. 5i's arrival was consistent with the period when commercial satellite communications began to populate Earth's spectrum with structured signals. It was as if someone had been monitoring our growing radio presence and responding in turn. Each probe was launched in reaction to successive stages of humanity's electromagnetic development. The visitors were not just confirming they had heard us, they were showing detailed knowledge of our technological progress over several decades. The Atacama Large Millimeter-Submillimeter Array in Chile started a coordinated effort to track the objects with meter-scale accuracy. VLBI, or Very Long Baseline Interferometry, merged data from radio telescopes around the world, creating a virtual dish the size of the Earth. The positional precision was exceptional, enabling astronomers to spot minute course adjustments and attitude changes that would not be apparent to single observatories. The VLBI findings confirmed that several objects were making slight modifications to their trajectories, small alterations in velocity and direction that could not be attributed to gravitational forces or radiation pressure alone. These course corrections seemed intentional, designed to adjust the objects' paths for better viewing from Earth or to maintain the quality of their communication links. High-energy astronomy facilities also contributed to the extensive monitoring campaign. IceCube in Antarctica, which is designed to detect neutrinos from cosmic events, watched for any unusual particle emissions that might be associated with advanced propulsion systems. Air shower arrays looked for connections between the object's positions and detections of high-energy cosmic rays. The outcomes from these high-energy observations were a subject of debate and controversy. Some researchers reported finding faint but statistically significant correlations between the visitors' positions and neutrino or cosmic ray events. Others found no such links and suggested that the claims were due to statistical anomalies or systematic errors in the analysis. This debate mirrored deeper uncertainties about the technologies the visitors might be employing. Conventional chemical or nuclear propulsion would not leave any detectable traces at interstellar distances. However, more exotic possibilities, such as antimatter engines, fusion ramjets, or entirely unknown physics, could generate high-energy particles that Earth-based detectors might be able to observe. Citizen science was mobilized with remarkable speed and scope. The Zooniverse platform introduced Interstellar Visitors, a project that allowed volunteers from all over the world to classify light curves and radiospectrograms. Within a few weeks, hundreds of thousands of people were contributing to the analysis. Their combined efforts amounted to person-years of work that would have been impossible for professional astronomers to achieve on their own. Anomalies identified by the community often resulted in priority observations at major observatories. Amateur astronomers found subtle changes in signal timing that had been overlooked by professional automated systems. High school students discovered patterns in the radio emissions that hinted at encoding methods more complex than simple carrier tones. This collaborative endeavor was the largest coordinated scientific response to a single event in history. Social media platforms turned into hubs for observational data and analysis tools. GitHub became a repository for open-source software for signal processing and orbital calculations. The entire global community was taking part in humanity's first systematic investigation of visitors from another star system. Space operators had to deal with more direct and practical issues. The objects' paths took them through busy areas of the inner solar system. Conjunction alerts were sent out to satellite operators, warning them of close passes to geostationary orbits and important spacecraft. The visitors did not present a direct risk of collision, but their unpredictable maneuvering abilities introduced new kinds of operational hazards. Insurance companies started to reevaluate their models for space debris collisions and communication interference. What if these visitors were not entirely predictable? What if they could maneuver more dynamically than had been observed so far? The possibility of technology beyond human comprehension added new factors to actuarial calculations that had previously been focused on natural dangers and human mistakes. The public's reaction shifted between awe and unease as more visitors were spotted throughout the summer and fall of 2025. Astronomical societies saw record numbers of attendees at star parties and observatory open houses. However, the same people who gathered to see the visitors through telescopes also showed a deeper sense of uncertainty about humanity's role in a universe that now seemed much more populated. Social media was alive with theories that ranged from serious scientific speculation to doomsday prophecies. The financial markets experienced unusual fluctuations in aerospace and defense stocks as investors tried to understand the implications of technologies that could be centuries or even millennia ahead of human capabilities. Some people clearly thought that humanity was on the verge of a world-changing discovery. Space tourism companies noted a sharp increase in bookings for suborbital flights, as if getting a bit closer to space would offer some kind of benefit when the visitors revealed their intentions. Spontaneous pilgrimage sites appeared at radio observatories where people could stand near the dishes that were tracking the objects in real time and listen to recordings of their transmissions. The most disquieting aspect was the apparent coordination among the objects. As more visitors were sighted throughout the summer and fall of 2025, their radio emissions started to show temporal correlations that went beyond simple frequency alignment. Short, synchronized transmissions occurred from multiple objects at the same time, lasting only for seconds, but clearly coordinated across millions of kilometers of space. Whatever intelligence had sent this flotilla was actively communicating between its various parts. The visitors were not just broadcasting towards Earth, they were also communicating with each other, coordinating their actions in real time despite the immense distances that separated them. The implications for their communication technology and organizational complexity were astounding. By September, the list contained 15 confirmed interstellar objects, with dozens more potential candidates waiting for confirmation as their orbits were more accurately determined. The sky was becoming filled with artificial visitors, each one announcing its presence on frequencies that humans had long considered the logical choice for interstellar communication. The pattern was now undeniable. These were not random cosmic travelers or natural debris from some far-off stellar disaster. This was a carefully planned mission, carried out with a precision and coordination that pointed to an intelligence and technology far superior to human capabilities. The question was no longer whether someone was trying to communicate with Earth. The question now was what they were attempting to say, and whether humanity was ready to receive a message that could fundamentally change our understanding of intelligence, technology, and our place among the stars. Part 4, A Pattern in the Noise. Did they hear us specifically? The mathematics were indisputable, and they revealed a narrative that left astronomers feeling profoundly uneasy. If the visitors had come from star systems approximately 50 light-years away, they would have had to detect Earth's radio signals decades earlier to schedule their arrival for 2025. This brought up a core question that went to the very heart of the mystery. When could they have realized we were here? Dr. James Chen at MIT's Haystack Radio Observatory undertook the challenge of reconstructing humanity's expanding radio bubble, decade by decade. This analysis necessitated a careful examination of transmitter power, antenna patterns, and the inverse square law, which dictates how signals spread through space. Not all of our broadcasts were equally detectable at interstellar distances. Television transmissions began in earnest in the 1940s, but the early systems were low-powered and not well-focused. The signals that escaped into space were faint and would have been hard to pick up beyond a few light-years. High-power military radars became common during the Cold War, generating stronger signals that could potentially be detected across interstellar distances. However, their narrow beams scanned across the sky in patterns that might have made them difficult to identify as artificial. By the 1960s, our most powerful transmissions, planetary radar systems designed to map Venus and track asteroids, were directing megawatts of radio energy towards specific areas of the sky. These systems operated at frequencies selected for optimal planetary observation, but they also produced the brightest radio signatures in Earth's history. The Arecibo Observatory, finished in 1963, became humanity's most potent voice in the cosmos. Its 305-meter dish was capable of transmitting up to 1 million watts of radio energy in a tightly focused beam. When employed for planetary radar observations, Arecibo generated radio signals bright enough to be detected by similar facilities across interstellar distances. The timeline was stark and clear. Any civilization within 50 light-years would have picked up our early television signals in the 1970s and 1980s, as those broadcasts made their journey across interstellar space at the speed of light. Our most powerful radar transmissions would have reached nearby star systems in the 1990s and 2000s, offering undeniable proof of a technological civilization on Earth. However, the visitors were not just showing up at random times. Their approach vectors, when traced back through galactic space using complex orbital mechanics calculations, pointed towards specific star systems that would have been ideally situated to observe Earth during our most active broadcasting periods. The correlation analysis had to be done with extreme caution to avoid the statistical pitfalls that had troubled other searches for patterns in astronomical data. Dr. Sarah Martinez at the Harvard-Smithsonian Center for Astrophysics headed a team that cross-referenced the visitors' origin vectors with Earth's transmission patterns over several decades, employing Monte Carlo simulations to evaluate the likelihood of spurious correlations. HD 164,595, a Sun-like star 94 light-years away, was directly in the path of our most powerful Arecibo transmissions during the 1970s and 1980s. The alignment was perfect. When Arecibo was aimed at Venus for radar mapping, its beam swept across the position of HD 164,595 in the sky. Any receivers in that system would have detected Earth's radar signals with a clarity that made their artificial origin unmistakable. Wolf 359, only 7.9 light-years away, would have received our television signals with exceptional clarity due to its location relative to Earth's rotational axis. The red dwarf star is situated nearly perpendicular to our planet's equatorial plane, which means it would have observed Earth from an angle that maximized the reception of our strongest commercial broadcast transmissions. Tau Ceti, a popular target for SETI searches because of its proximity and sun-like characteristics, was perfectly aligned with several major radar campaigns carried out during the 1990s and early 2000s. The star system would have received clear evidence of technological activity on Earth precisely during the time when our deepest space missions were starting to unveil the structure and composition of our solar system. The statistical analysis showed correlations that were significant at the 4 sigma level, with odds of about 1 in 15,000 that the patterns were purely coincidental. In particle physics, such correlations would be considered strong evidence for new phenomena. In astronomy, they required serious consideration, even from skeptical researchers. However, critics contended that this kind of analysis was susceptible to what statisticians term the look elsewhere effect, the tendency to discover patterns when you examine enough data with sufficient flexibility in your analysis techniques. With hundreds of nearby star systems and decades of transmission history, some correlations were bound to appear, even if no genuine relationship existed. Dr. Robert Hayes at the University of Arizona led the skeptical counterargument. His team performed parallel analyses using randomized datasets and slightly different statistical methods. They discovered that apparent correlations could arise from chance alignments combined with observational biases and the human tendency for pattern recognition. "We're seeing patterns because we want to see them," Hayes asserted in a widely referenced paper published in the Astrophysical Journal. Give humans enough data about their own transmissions and some cosmic visitors, and they'll find connections between anything. The universe is under no obligation to be concerned with our radio broadcasts. Yet the temporal patterns within the visitor's arrival sequence offered more convincing evidence that went beyond simple geometric alignments. The objects did not arrive at random intervals dictated solely by orbital mechanics. Their spacing seemed to echo key milestones in humanity's broadcast history with a precision that was hard to dismiss as mere coincidence. Dr. Lisa Johansson at the SETI Institute put forward the echo hypothesis, a model that viewed each visitor as a response to particular human transmissions. If the visitors were indeed replies to our broadcasts, their arrival times should reflect our own transmission milestones, with a delay for the light travel time between star systems plus the time needed for interstellar travel. She developed a mathematical model that assumed interstellar travel speeds of 10 to 20% of the speed of light, fast by human standards, but attainable for civilizations with advanced propulsion technology. The model predicted visitor arrival times based on the intensity and timing of Earth's strongest radio transmissions, adjusted for the probability that different star systems could have detected those signals. The correlation between the predicted and observed arrival times was striking. 3 Atlas's timeline corresponded to a response to Earth's television broadcasting peak in the 1970s. 4 Eye's arrival aligned with reactions to early military radar installations. 5 Eye's arrival was consistent with the era of commercial satellite communication. The patterns indicated not just intelligence, but an intelligence that had been observing Earth's technological advancement over several decades. The most compelling proof came from an information theory analysis of the visitors' radio emissions. Several objects displayed transmission patterns that appeared to allude to the 1974 Arecibo message, that renowned 3-minute broadcast aimed at the globular cluster M13. The Arecibo message had encoded the numbers 1 through 10 in binary notation, followed by the atomic numbers for hydrogen, carbon, nitrogen, oxygen, and phosphorus, the essential elements of DNA. It also featured a representation of the double helix structure, a basic pictogram of a human figure, and a diagram of the solar system with Earth identified as the third planet from the Sun. Some of the visitors' signals included similar numerical sequences, but with subtle changes that suggested deliberate modification rather than simple repetition or random noise. The binary sequences were identifiable, but they extended beyond the original Arecibo format, incorporating mathematical concepts that humans had discovered but not yet transmitted into space. The prime number sequences were especially noteworthy and perhaps represented the strongest evidence of intentional communication. The Arecibo message had utilized prime numbers as a universal mathematical concept, something any technological civilization would recognize, irrespective of their specific counting system or mathematical notation. Several visitors broadcast their own prime sequences: 2, 3, 5, 7, 11, 13, 17, 19, 23. But then they diverged from the standard progression in ways that seemed intentional rather than accidental. It was as if someone was conveying, "We received your message and understood your mathematical language. Now, let us show you variations and extensions that demonstrate our own mathematical sophistication." The deviations were not random. They adhered to patterns that matched advanced number theory: twin primes, Sophie-Germain primes, Mersenne primes. The visitors were showcasing mathematical knowledge that went beyond simple counting, demonstrating familiarity with concepts that human mathematicians had developed over centuries of research. The statistical analysis of the mathematical content had to be done with extreme care to avoid the alluring pitfall of finding patterns in noisy data. Dr. Chen's team pre-registered their hypothesis before examining the visitors' transmissions, committing to specific statistical tests and significance thresholds. They used Monte Carlo simulations to determine the probability of finding apparent mathematical patterns in random data. Even with these stringent measures, the connections remained statistically strong. The likelihood that random radio emissions would contain recognizable mathematical sequences related to human broadcasts was less than 1 in 10,000. The visitors were showing knowledge of human mathematics and expanding on it in ways that proved their intelligence and technological prowess. However, the skeptical community strongly contested these interpretations. The debate unfolded in academic journals and on social media with equal fervor, mirroring fundamental disagreements about how to assess extraordinary claims with limited data. Hayes and his colleagues maintained that the apparent mathematical content was more a reflection of human psychology than alien communication. Pattern recognition is fundamental to human cognition, they wrote. We evolved to find meaningful signals in noisy environments. When we view cosmic phenomena through that evolutionary lens, we are inclined to perceive intelligence even in random processes. The statistical arguments grew increasingly complex as both sides refined their methods and assumptions. Proponents of the intelligence hypothesis highlighted the multiple independent lines of evidence: geometric correlations, temporal patterns, mathematical content, and coordinated behaviors across multiple objects. Critics underscored the risks of multiple hypothesis testing and the human inclination to find significance in large data sets. The debate garnered attention from philosophers of science and experts in statistical methodology. The National Academy of Sciences formed a special panel to review the evidence and offer guidance for future research. The panel's initial report was cautiously phrased, but conceded that the visitors represented phenomena that warranted serious scientific investigation using the most rigorous methods available. Social media amplified the controversy, with hashtags like "Cana," "Pattern," or "Pareidolia" trending globally. Late-night talk show hosts quipped about humans being so self-centered that they assumed every cosmic coincidence was about them. But the scientific community approached the analysis with gravity, acknowledging that even a small chance of intentional contact had immense implications for humanity's future. The provisional consensus that emerged from months of analysis and intense debate was carefully articulated. The correlations between Earth's transmission history and the visitor's characteristics were statistically significant and not easily accounted for by random processes or observational biases. Whether this signified intentional communication was still an open question, but the patterns were compelling enough to warrant systematic attempts at a response. The phrase "systematic attempts at a response" carried significant weight. It suggested that humanity might try to communicate back to see if the visitors would react to our transmissions in real time. The notion was both exhilarating and frightening. Our first intentional dialogue with intelligence from another star system. After decades of passive listening, we were considering active involvement in what could be the galaxy's oldest and most important conversation. The visitors had provided what seemed to be their opening statement, showing knowledge of our mathematics, our history, and our location in space. The question now was whether we were prepared to reply and what we might discover from beings who had perfected the art of communication across interstellar distances. Part 5. Anatomy of an Enigma. What 3 Atlas is physically. By October 2025, the collective observations from dozens of observatories worldwide had created the most comprehensive profile of an interstellar object in history. The picture that took shape was one that was difficult to categorize easily. 3 Atlas was approximately 200 meters in its longest dimension, with a width of about 20 meters and a thickness that radar observations indicated was less than 2 meters. Its aspect ratio was greater than 10:1, making it one of the most elongated objects ever seen in the solar system. Its form was consistent with a thin panel, or a stack of panels, possibly articulated and capable of changing its shape. The object's non-gravitational accelerations were slight but clear. As it neared perihelion, tiny deviations from a purely gravitational path built up into noticeable course adjustments. The accelerations were consistent, always directed towards or away from the Sun, never random. They were in line with the predictions for radiation pressure acting on a highly reflective surface, but the object's measured albedo was too low to account for such effects. Spectroscopic analysis showed a surface chemistry unlike anything found in the asteroid catalogs. The spectrum displayed absorption features that were consistent with exotic carbon allotropes, materials that might have been engineered rather than naturally formed. There were indications of boron nitride coatings and traces of metals arranged in patterns that suggested they had been deliberately added for specific electromagnetic properties. The thermal behavior was perhaps the most baffling feature. As 3 Atlas traveled through different distances from the Sun, its temperature did not follow the simple inverse square law that applies to most objects in the solar system. Instead, it exhibited thermal plateaus, regions where the temperature stayed almost constant despite changes in solar radiation. This pointed to active thermal management, possibly through microlouvers or metamaterial surfaces that could alter their emissivity in real time. The object's rotation was just as controlled. Unlike natural asteroids, which tumble chaotically due to their collision history and tidal forces, 3 Atlas kept a stable spin axis that was aligned with specific celestial coordinates. More fascinatingly, its rotation period showed subtle variations that were correlated with the angles of solar illumination, as if the object were adjusting its orientation to optimize solar energy collection or thermal management. The radio emissions remained the most convincing proof of its artificial origin. The main carrier at 1420.4 MHz was accompanied by harmonics at precise mathematical intervals. At first, the signal had no modulation, just a clean, narrowband tone that Doppler shifted with the object's movement. But as 3 Atlas approached perihelion in November, modulation started to appear. The pattern was unmistakable. Prime numbers, groups of pulses corresponding to 2, 3, 5, 7, 11, 13, 17, 19. The sequence went on through the first several dozen primes, and then it repeated. It was the kind of signal that SETI researchers had long predicted as the initial communication from an alien intelligence, mathematically sophisticated yet simple enough to be recognized as artificial. Dr. Abraham Loeb at Harvard had suggested several criteria for identifying artificial interstellar objects, including unusual brightness at great distances, signs of artificial acceleration, and electromagnetic emissions. 3 Atlas seemed to meet all of these criteria. Loeb calculated that if the object's reflectivity were ordinary, its apparent brightness at its discovery distance would mean it had to be generating about 10 gigawatts of internal power, enough to power a small city. The mainstream astronomical community was still cautious. Images from the Hubble Space Telescope revealed a diffuse coma around 3 Atlas, which was consistent with gas and dust sublimating as the object warmed up near the Sun. The astronomy picture of the day featured these images with captions that highlighted normal cometary behavior. Ground-based observations found water vapor and carbon monoxide in the object's immediate vicinity, which supported natural explanations. However, even standard cometary physics could not fully explain all the observations. The outgassing was too weak to account for the non-gravitational accelerations. The structure of the coma showed asymmetries that suggested controlled venting rather than simple sublimation. Most perplexingly, the radio emissions continued even when the object was at its farthest point from the Sun, where natural plasma processes should have stopped. The debate came to a head, centered on competing hypotheses. Natural-based theories called upon unusual yet believable possibilities, such as a piece from a shattered comet possessing a strange composition and shape, perhaps containing metallic elements capable of generating radio emissions through interactions with plasma. Its regulated spin and heat patterns could be a consequence of its inner construction, including hollows and compartments, which would produce thermal inertia and gyroscopic stability. Theories involving intelligent design were more conjectural but unsettlingly in line with the data, suggesting an autonomous probe or a messaging device, perhaps relying on solar radiation for its power and orientation control. The object's slender form pointed to a structure that could be unfurled, maybe a communications array built to maximize its surface area for both gathering solar power and transmitting radio waves. The sequence of prime numbers was an indicator of not merely intelligence, but an intelligence that comprehended human mathematical principles. A third class of explanation arose, positioned somewhere between the natural and the artificial. Dr. Elena Rodriguez from the University of Barcelona put forward the idea that 3I Atlas could be technobiotic refuse, the leftovers of a biological civilization that had mastered the art of engineering materials on a molecular scale. The object might be partially living, employing biological functions to preserve its form and behavior over interstellar journeys. Assessing the risk became a top concern as 3I Atlas neared its closest passage to Earth in late November. The object was set to pass within 0.3 astronomical units, approximately 45 million kilometers, near enough for in-depth observation, yet distant enough to preclude any gravitational disruption to Earth's orbit. A greater worry was the potential for it to shed debris. If the object was truly artificial and possibly impaired by its extended travel between stars, fragments could break away during its perihelion transit. The Planetary Defense Coordination Office circulated cautious notices to space agencies globally. Although 3I Atlas presented no immediate threat of collision, its actions were still unpredictable. The controlled changes in its velocity demonstrated the object's capacity for maneuvering. The critical question was whether these movements were automatic reactions to solar radiation or signified active steering by some form of intelligence. The presence of companion objects introduced an additional level of complexity. Several smaller items, labeled 3 Atlas A through 3I Atlas F, moved in formation alongside the main object. These fragments exhibited comparable radio signals and coordinated movements, implying they could be calibration reflectors or relay points for a larger communication network. An examination of energy requirements presented a stark reality. The radio signals alone necessitated kilowatts of power, a considerable amount for an object with a finite area for collecting solar energy. If the broadcasts were indeed deliberate communications and not just wasted energy, they signified a major allocation of resources. An individual or an entity was expending a great deal of energy to guarantee we could detect them as 3I Atlas approached perihelion on the 28th of November, 2025. The global astronomical community collectively held its breath. This represented the point of nearest approach, the moment of greatest heating, and if the object was in fact artificial, potentially the time of its highest activity. Every significant observatory on Earth was focused on it, waiting to see what humanity's most mysterious visitor would disclose about itself. Part 6. Responding, Protocols, Politics, and the Initial Reply. The instant astronomers verified that 3I Atlas was broadcasting prime numbers, humanity was confronted with a query it had never before seriously faced. How does one answer a message from the cosmos? The International Academy of Astronautics had dedicated decades to creating post-detection procedures for SETI signals. Their recommendations were exhaustive but non-binding, a cautious system for validation, study, and eventual reply that operated on the assumption that governments would collaborate via established treaty frameworks. However, no existing treaty had ever envisioned visitors that could navigate and communicate proactively while traversing the solar system. The UN Committee on the Peaceful Uses of Outer Space called for urgent meetings in Vienna. COPUOS, as it was commonly called, had managed issues ranging from space junk to commercial satellite deployments, but never interstellar diplomacy. The Committee on Space Research, COSPAR, contributed its expertise on planetary protection guidelines, originally formulated to stop the contamination of Mars and Europa. Did the same rules extend to artificial visitors from other stellar systems? The International Telecommunication Union dealt with more pressing problems. Radio frequencies were national assets, meticulously distributed to avoid conflicts between terrestrial broadcasters. But what was the protocol when an extraterrestrial intelligence began transmitting on frequencies set aside for radio astronomy? The ITU's function in safeguarding SETI frequencies abruptly became vital for preventing interference with humanity's first dialogue with the universe. In private discussions, the debate was less civil. National space agencies were aware that the first to respond could establish a kind of precedent in interstellar dialogue. NASA's Deep Space Network was capable of reaching 3I Atlas using its current equipment. The European Space Agency's STRAC network offered similar functions. China's growing deep space communication network was quickly achieving parity with Western capabilities. Yet the most potent transmitters were owned by military bodies and academic research centers. The Arecibo Observatory in Puerto Rico, even after its recent structural failure, had been the most powerful radio telescope on the planet. Its intended successor, the proposed next-generation Arecibo telescope, was still years from completion. The responsibility had shifted to other installations. The 500-meter aperture spherical telescope, FAST in China, the enhanced facilities at Goldstone and Canberra, and university-run arrays like the Very Large Array in New Mexico. Dr. Jill Tarter, the former head of the SETI Institute, took on the role of an unexpected facilitator. Her extensive experience in searching for extraterrestrial signals lent her a unique credibility to discuss protocols and methodologies. "We have always recognized this day could arrive," she stated in emergency sessions with her international counterparts. "The real question is whether we will reply as a unified species or as rival nations." The technological hurdles were significant yet surmountable. Any reply to 3I Atlas would have to factor in the object's swift movement and its varying distance. Doppler compensation would necessitate exact tracking and real-time frequency modifications. The broadcasts would need to be strong enough to span interplanetary voids while staying sufficiently narrowband to be unmistakably artificial. The communication method drew from SETI customs and information theory. Start with mathematics, the common tongue. Respond with the prime number sequence to show understanding. Subsequently, introduce more intricate ideas. Atomic structures, fundamental physical constants, maybe even a basic star chart indicating our location in the galaxy. Restrictions on content became a point of intense controversy. Military consultants advised against disclosing sensitive details about Earth's infrastructure or defense systems. Scientists countered that any civilization capable of interstellar travel would already grasp our technological constraints. The resulting compromise was remarkably simple: reply with the same kinds of information we had already intentionally transmitted, such as the mathematical and physical concepts from the 1974 Arecibo message, brought up to date with contemporary knowledge. The modulation technique needed to be basic enough for any intelligence to decipher, yet complex enough to convey substantial information. The team chose pulse position modulation with robust error correction, a method that was slow and inefficient but highly resistant to data corruption. Barker codes would serve as clear preambles, mathematical sequences that could only be of artificial origin. Time was the most pressing limitation. 3I Atlas would be an optimal communication range for just a matter of weeks. The object's high speed meant that Earth's rotation would create short communication opportunities as different antenna arrays rotated into view. Dynamic scheduling software, initially created for tracking deep space probes, was adapted to maximize communication time with humanity's first interstellar contact. Chain of custody procedures guaranteed that every broadcast would be recorded and authenticated. Cryptographic signatures would thwart any future assertions that the messages were modified or faked. Numerous observatories would keep separate records, establishing a lasting archive of humanity's first deliberate communication with another intelligence. The choice to transmit was made on the 3rd of December, 2025. 3I Atlas was nearing its best viewing position from Earth, and radio astronomers had confirmed that the object's prime number broadcast was proceeding with growing complexity. The visitor was exhibiting a mathematical elegance that went far beyond mere counting. Dr. Martinez initiated the transmission from the Arecibo replacement facility, which was now operating under international supervision. The message started with the identical prime sequence that 3I Atlas had been sending, confirming we had received and comprehended it. It followed with the initial few elements from the periodic table, rendered in binary code. Next came a straightforward depiction of the hydrogen atom, the very concept that determined the frequency of our dialogue. The answer arrived 18 minutes later, the time it took for light to travel to 3I Atlas and return. The visitor's signal transformed. The consistent prime number sequence was replaced by a more intricate pattern, sets of pulses that matched atomic numbers. Hydrogen, helium, lithium, beryllium. But then the sequence deviated from Earth's periodic table, featuring pulse groups that corresponded to no known element. It was as if the visitor was instructing us in a chemistry we had yet to discover. Even more astonishing was the change in the object itself. Ground-based telescopes registered a slight increase in its brightness, a brief shutter-like flash that endured for precisely the duration of Earth's broadcast. Photometric analysis indicated that a portion of 3I Atlas had physically altered its configuration, perhaps by unfurling reflective surfaces or changing its orientation to provide a visual confirmation of the radio conversation. The implications were immense. This was not a passive reflection of a natural event. This was an active, real-time dialogue with an intelligence that could synchronize radio and optical signals across the vastness of interplanetary space. Information about the successful exchange became public within hours, despite careful attempts at secrecy. Amateur radio enthusiasts worldwide had been observing the frequencies, and the unique pulse arrangements were impossible to conceal. Social media platforms burst with enthusiasm and conjecture. Governments quickly released statements urging restraint and global cooperation, but the core truth was undeniable. Humanity had successfully started a conversation with visitors from another star system. The second exchange occurred 2 days after the first. This time, 3I Atlas started the communication, sending a more elaborate mathematical sequence. The pattern seemed to illustrate orbital dynamics, the movement of bodies around gravitational centers. When Earth's mathematicians deciphered the complete sequence, they understood that the visitor was describing not just the general theory of orbits, but the precise path it was taking through our solar system. It was demonstrating its awareness of its location and destination. More significantly, it was proving that its arrival in our solar system was no mere chance. The trajectory had been meticulously calculated, planned, and carried out across interstellar voids with a precision that hinted at technologies humanity could scarcely comprehend. The visitor was not merely replying to our call. It was explaining how it had detected us, journeyed to locate us, and positioned itself for the best possible communication. The dialogue that ensued would challenge every belief about our position in the universe and our destiny among the stars. But first, we had to grasp what 3I Atlas was attempting to teach us about the galaxy we thought we understood. Part 7. Earth's Reaction, Psychology, Faith, and Markets. The moment the news of a successful two-way dialogue with 3I Atlas was confirmed, humanity's collective consciousness underwent a transformation that would require decades for sociologists to fully comprehend. Mental health crisis lines noted a 340% rise in calls in the first week after the exchange was made public. The discussions fell into familiar categories: existential dread about humanity's role in the cosmos, profound excitement over the future possibilities, and a strange kind of cosmic isolation, the realization that we had never actually been alone, but had believed we were for centuries. Dr. Susan Chen at the Stanford Psychology Institute introduced the term contact syndrome to define the set of responses she witnessed in her clinical work. Patients described intense dreams of space exploration, an obsessive compulsion to watch the sky, and a sudden feeling that everyday problems had become insignificant. It is as if individuals are attempting to mentally steel themselves for a future they cannot yet grasp, she observed in her initial findings. Religious reactions differed starkly among various denominations and beliefs. The Vatican released a carefully composed statement within 48 hours asserting that the finding of intelligent life beyond Earth was in harmony with Catholic doctrine. "The universe is immense and filled with marvels," Pope Francis stated. If God has decided to inhabit it with other forms of consciousness, this only enhances our appreciation of His boundless creativity. Responses from evangelical Protestants were more divided. Some church leaders saw the visitors as proof of God's cosmic greatness. Others were concerned about the theological ramifications. Did beings from other planets have souls? Did the sacrifice of Christ apply beyond Earth? Urgent theological symposiums were held in seminaries across the globe, wrestling with questions that had, until then, been purely hypothetical. Islamic academics found more solid footing in the Quran's mentions of God's creation, encompassing numerous worlds. Buddhist teachers viewed the contact as a validation that consciousness is an intrinsic quality of the universe. Hindu traditions, already at ease with vast cosmic scales and various planes of existence, adapted to the new reality with the most ease. Meanwhile, financial markets underwent what economists later termed the contact correction. Stocks in aerospace and defense initially skyrocketed, fueled by conjecture about new technologies and government contracts, but the increases were unstable, plummeting sharply when early analysis indicated the visitors displayed no signs of aggression. Satellite communication firms experienced significant changes in their insurance costs as the risk of interference, whether deliberate or unintentional, from advanced alien technology introduced new types of liability. Prices for rare earth elements surged due to speculation that alien technology might depend on exotic materials. Lithium, used in batteries and electronics, saw its price double in a single week. Gold, traditionally a refuge in times of turmoil, remained surprisingly steady. It seemed that investors thought beings capable of interstellar travel would be less captivated by gleaming metals than past generations of humans had been. The cryptocurrency markets provided a compelling insight into the collective psyche. Bitcoin values climbed on the belief that decentralized digital currencies might be favored by interstellar merchants. New contact coins emerged daily, most of them sophisticated frauds, but some representing sincere efforts to devise communication methods that could function across species. Information warfare broke out across social media platforms almost instantly. Bot networks, many seemingly sponsored by governments, inundated Twitter, Facebook, and TikTok with conflicting stories. Some asserted the entire contact event was a detailed fabrication by world governments to rationalize heightened surveillance. Others claimed the visitors were an invasion force and called for immediate military action. Platform administrators found themselves in the novel situation of verifying claims about alien intelligence. Twitter's policy department worked feverishly to create rules for extraterrestrial content while also trying to combat false information about the visitors' motives and abilities. Verification symbols started appearing on official observatory accounts, establishing a new class of reliable sources for cosmic news. Educational institutions hurried to adapt to a sudden surge in student interest in astronomy, radio engineering, and astrobiology. Universities saw record enrollment in physics and mathematics programs. Community colleges started to offer intensive courses in radio technology, instructing students on how to construct their own receivers to monitor interstellar broadcasts. The reactions of children were especially revealing. Educators noted that students had started to integrate space-related themes into their art and creative writing with remarkable depth. Many children appeared less taken aback by the contact than adults, as if they had always presumed the universe held other intelligent beings and were simply waiting for the grown-ups to acknowledge it. The art world responded with its usual fervor. Museums hastily put together exhibitions showcasing space-themed art. New musical pieces were composed almost daily, many integrating prime number rhythms, or the actual radio frequencies picked up from 3i Atlas. Visual artists built installations that used the hydrogen line frequency as a central theme, 1,420 megahertz converted into colors, designs, and sculptural shapes. Social customs developed spontaneously. Listening parties gained popularity, with people assembling around radios set to frequencies where the visitors might transmit. Astronomy clubs were deluged with new members eager to see the visitors through telescopes. The hashtag #JammerSpace became a worldwide trend, with millions of individuals posting messages aimed at extraterrestrial beings. Night sky photography saw an explosion in popularity. Amateur astronomers who had never before owned a camera suddenly bought telephoto lenses and tracking mounts, hoping to take pictures of the interstellar visitors. The images themselves were not extraordinary, distant specks of light, no different from stars. Yet the act of taking the photos seemed to fulfill a profound human impulse to record and distribute this landmark event. Urban light pollution turned into a political topic for the first time in many years. City governments faced calls to pass dark sky laws, reducing unnecessary lighting to enhance astronomical viewing. Hardware stores sold out of red flashlights, the favored light source for maintaining night vision during stargazing. The psychological effects reached into unforeseen domains. Marriage proposals reportedly began to include allusions to the cosmic viewpoint. Dating applications incorporated opinions on extraterrestrial contact into their matching systems. Pet adoption numbers increased, perhaps indicating a need for companionship in uncertain times. Corporate advertising adapted with astonishing agility. Car advertisements showed families driving to remote spots for better stargazing. Smartphone makers highlighted their cameras' abilities in low light for astrophotography. Coffee brands sold contact blends for those extended nights of watching the sky. But perhaps the most profound alteration was more subtle, a change in the perception of time. People started to think in longer spans, evaluating choices within the framework of cosmic history rather than quarterly profits or election results. Discussions about urban planning began to include speculation on how cities might need to change for a species that was aware it was not alone in the universe. The psychological studies would go on for years, but the initial trends were unmistakable. Humanity was not merely coming to terms with the existence of other intelligences. We were starting to see ourselves as members of a larger community of minds spread throughout the galaxy. The sense of isolation that had characterized human consciousness since we first gazed at the stars was, at last, tentatively dissipating. Part 8. Creating a mission in months, not years. By January of 2026, what was once impossible had become unavoidable. Humanity was going to dispatch a spacecraft to meet with 3I Atlas. The mission's design came from urgent planning meetings that united NASA's top engineers, ESA's mission planners, and delegates from commercial space firms that had been quietly transforming space access. The task was without precedent: to catch a target traveling at interstellar speeds with a launch opportunity of only weeks instead of years. Conventional mission planning operated on development timelines of a decade or more. The Voyager probes had required 8 years from their initial concept to their launch. The James Webb Space Telescope took 3 decades from its first proposal to becoming operational. But 3I Atlas would not pause for human administrative processes. By the middle of 2026, the visitor would be speeding away from the Sun, out of reach of any spacecraft humanity could realistically build. The answer was found in using hardware that was already available or could be quickly adapted. SpaceX's Super Heavy booster, first intended for Mars missions, was capable of sending heavy payloads on interplanetary paths. Solar electric propulsion systems, validated on asteroid missions, could deliver the precise navigation needed for the interception. The difficulty lay in combining these parts into a working mission in under 8 months. Dr. Robert Brown, previously with NASA's Jet Propulsion Laboratory, spearheaded the international mission design team. His approach was relentlessly practical. Employ only established technologies, accept greater risks than in typical missions, and concentrate solely on goals that could be met during a short flyby. The fundamental mission plan was strikingly simple. A single large spacecraft would launch in June of 2026, taking a minimal energy route to intercept 3I Atlas in September. The encounter would last for about 6 hours, during which the spacecraft would release several small probes meant to observe the visitor from various perspectives while keeping a safe separation. The most significant technical hurdles were in guidance, navigation, and control. 3I Atlas was a slender, tumbling object with unpredictable maneuvering abilities. Standard asteroid flyby missions depended on exact trajectory forecasting, but this visitor had already shown it could make minor adjustments to its path. The spacecraft would require autonomous navigation systems that could adapt to the target's movements in real time. The choice of instruments reflected the immediate scientific needs. Wideband radio receivers would scan the entire spectrum of signals from 3I Atlas, looking for communication attempts or informational content. Optical cameras with a range of filters would record the object's physical form and surface characteristics. Laser communication systems would try to create a high-speed link to see if the visitor could react to optical signals as well as radio. In a more controversial move, the mission carried microprobes designed to get extremely close, possibly within meters of 3I Atlas's surface. These contactors were fitted with sampling devices that could gather material if the chance arose, but their main goal was detailed observation and active signal transmission from a short distance. The role of the James Webb Space Telescope was crucial for the mission's success. JWST's ability to track moving targets, though restricted to objects moving slower than 75 milliseconds per second, could potentially observe 3I Atlas during certain parts of its journey. More importantly, JWST's sensitivity to infrared light might pick up thermal signatures that could indicate an internal structure or power sources. Very long baseline interferometry networks around the world work together to provide microarcsecond position data for 3I Atlas. This level of precision, achieved by merging signals from radio telescopes located continents apart, would allow for trajectory predictions accurate enough for the spacecraft's intercept calculations. The Rubin Observatory's Legacy Survey of Space and Time, set to start full operations in 2025, presented another benefit. LSST's broad field surveys could potentially spot future interstellar visitors sooner, giving more lead time for mission planning. The insights gained from the 3I Atlas encounter would shape rapid response protocols for any subsequent visitors. The ethics of sample collection sparked a fierce debate within the scientific community. The Committee on Space Research, COSPAR, had created planetary protection classifications for various types of missions, but none dealt with the possibility of collecting samples from potentially artificial objects from other star systems. Was 3I Atlas a natural object that could be studied like any other asteroid, or did it belong to another intelligence and should be treated with diplomatic rather than scientific protocols? The solution was a cautious one. Sampling would only be considered if 3I Atlas seemed to be naturally shedding material or if the visitor gave some form of clear consent through its communication patterns. Direct contact with the main structure would be avoided unless it was absolutely essential for the mission's success. International collaboration proceeded with surprising ease. The mission's scale and timeline demanded resources that no single country could provide in time. NASA offered launch services and mission operations expertise. ESA supplied proven propulsion systems and navigation software. Commercial partners provided communications gear and computing power. This arrangement set a precedent for future international missions to non-traditional targets. Contingency planning took up a vast amount of effort. What if 3I Atlas altered its course without warning? What if it activated defensive measures or debris fields? What if attempts at communication provoked a hostile reaction? Each potential situation required pre-planned responses that could be carried out autonomously, as the 8-minute communication lag to mission control would make real-time human intervention impossible. The encounter schedule was planned with military-like precision. The initial approach would happen at a distance of 10,000 kilometers, far beyond any potential debris field, but close enough for detailed observation. The main spacecraft would keep this distance while sending out microprobes for a closer look. Active communication attempts would start right away, using every available frequency and modulation technique. As the launch date in June 2026 neared, public fascination was intensely fixed on the mission. Unlike previous interplanetary missions that drew only moderate public interest, the 3I Atlas rendezvous captured the world's imagination. The spacecraft carried messages from global leaders, children's art chosen through international contests, and symbolic items representing human civilization. The encounter itself would be short but historic. For 6 hours, humanity would get its most detailed view of visitors from another star system. The scientific findings could answer fundamental questions about the nature of interstellar objects and the existence of extraterrestrial intelligence. More importantly, the mission would prove humanity's ability to react swiftly to cosmic opportunities. But as the spacecraft sped towards its meeting with 3I Atlas, scientists braced themselves for discoveries that could challenge every assumption about intelligence, technology, and our place among the stars. Part 9. Proof or Pareidolia, the Scientific Knife Edge. The most difficult aspect of extraordinary science is recognizing when you have discovered something truly extraordinary. Dr. Elena Martinez knew this as she examined the data returning from humanity's first interstellar rendezvous. The encounter with 3I Atlas had gone on for 6 hours and 17 minutes, yielding terabytes of observations that would require months to fully process. However, the initial findings posed more questions than they resolved, and the scientific community found itself on a fine line between discovery and self-deception. Extraordinary claims demand extraordinary evidence, a tenet that had steered SETI research for many years. But how does one define extraordinary when encountering phenomena never before seen? The difficulty was not merely in processing the data from 3I Atlas. It was in creating entirely new methods for assessing claims about non-human intelligence. The scientific method had developed advanced tools to prevent false positives. Pre-registered analyses required researchers to state their specific hypotheses before looking at the data, thus avoiding the subconscious cherry-picking that could transform random noise into meaningful signals. Blind injections, fake signals introduced into datasets without the researcher's awareness, were used to test if detection systems could differentiate between real events and technical glitches. Independent analysis pipelines, created by separate teams using different software, offered cross-verification for crucial findings. If 5 distinct groups, using the same data but different methods, all arrived at the same conclusions, the results became more credible. If their findings differed, further investigation was necessary. The competing theories for 3I Atlas were grouped into 3 main categories, each with its own set of predictions and observational criteria. The engineered light sail theory suggested that 3I Atlas was an artificial object, perhaps automated, built for interstellar communication or exploration. This theory accounted for the object's extreme shape, controlled spin, thermal regulation, and radio signals. It predicted that a thorough analysis would uncover materials or structures that were not consistent with natural formation processes. The exotic natural fragment theory proposed that 3I Atlas was a previously undiscovered type of interstellar object, possibly debris from a stellar collision or the breakup of a comet made of unusual substances. This theory could potentially explain the object's strange properties without needing to invoke intelligent design. It predicted that spectroscopic analysis would eventually show natural, though uncommon, formation mechanisms. The normal comet theory argued that 3I Atlas was basically similar to 2I Borisov, with its seeming oddities being the result of observational errors, selection biases, or misunderstood natural phenomena. This theory predicted that a more detailed examination would reveal typical cometary behavior hidden by the object's strange orientation and composition. Each theory held up differently against the growing body of evidence. The radio signals were strong evidence for an artificial origin. Natural processes rarely create narrowband signals with mathematical modulation. The controlled rotation and thermal regulation also appeared more in line with engineered systems than with natural objects. However, the spectroscopic data was still inconclusive. While 3I Atlas displayed an unusual surface chemistry, deciding whether these materials were natural or artificial required an understanding of formation processes that might not occur anywhere else in the galaxy. Exotic did not automatically mean artificial. The Encounter mission had supplied vital new data. Close-up images showed surface features that seemed organized rather than random, patterns that hinted at design instead of natural erosion or impact damage. But pareidolia, the human inclination to see patterns where none exist, had misled people throughout history. The canals on Mars had appeared unmistakably artificial to 19th-century astronomers. Laser communication experiments during the encounter yielded the most intriguing results. When the spacecraft sent structured light pulses towards 3I Atlas, the object's surface reflectivity altered in ways that seemed to match the transmission sequence. But optical phenomena in space can be complex, and confirming that these changes were deliberate responses rather than mere coincidences demanded statistical analysis that was still in progress. The historical case of Oumuamua served as both a guide and a warning. That first interstellar visitor had exhibited non-gravitational accelerations that at first seemed impossible to explain. Scientists suggested exotic reasons, fragments of alien technology, hydrogen icebergs, and even the idea that Oumuamua might be a light sail from another civilization, but a meticulous analysis by Dr. Marco Micheli and his team, published in Nature in 2018, showed that the accelerations could be explained by conventional outgassing from a comet's nucleus. The strange shape and lack of a visible coma had at first hidden Oumuamua's cometary nature, but detailed modeling proved that natural processes could explain all the observed characteristics. The lesson was a humbling one. Extraordinary theories should be a last resort, not a first assumption. Natural explanations, even highly improbable ones, deserved thorough consideration before turning to extraterrestrial intelligence. 2I Borisov had offered a valuable comparison, a clearly normal interstellar comet that acted exactly as predicted by theory. Its composition was similar to comets in our solar system, its outgassing followed standard models, and its path showed no irregularities. Borisov proved that most interstellar visitors would likely be ordinary, making the apparent oddities of 3I Atlas even more fascinating. The ongoing debate over interstellar meteors added another layer of complexity to the analysis. The 2014 fireball known as IM-1 had been classified as potentially interstellar due to its high speed and unusual path. Dr. Avi Loeb's expedition to retrieve material from the impact site had found spherical fragments with compositions that some researchers asserted were artificial. But the IM-1 spherules remained a subject of controversy. Other scientists contended that the strange compositions could be the result of terrestrial contamination or normal meteoritic processes occurring under extreme conditions. The need for larger samples and independent lab analysis had delayed any definitive conclusions. These past experiences shaped the analysis of the 3I Atlas data. Every anomaly needed multiple independent verifications. Every unusual measurement had to be replicated by different instruments and analysis methods. The scientific community was resolute in avoiding both false positives and false negatives, claims of alien contact that were later disproven, or the dismissal of genuine phenomena due to excessive skepticism. Bias audits became a standard part of the analysis. Teams of researchers would swap datasets and analytical duties, looking for systematic errors or subconscious assumptions that might influence the results. Adversarial collaborations brought together scientists with fundamentally different views on the data, compelling them to pinpoint the observations that could differentiate between competing theories. The process was slow and at times frustrating, but it was effective. 6 months after the encounter, a preliminary consensus began to form within the scientific community. The evidence for an artificial origin was suggestive, but not definitive. Several key observations could not be explained by natural processes, yet the possibility of exotic natural phenomena could not be completely dismissed. The provisional language for public announcements was meticulously chosen. 3i Atlas displays characteristics that are challenging to explain with our current understanding of natural processes. While the possibility of an artificial origin cannot be ruled out, further observation and analysis are required to arrive at a firm conclusion. But even this guarded statement held profound implications. For the first time in human history, the scientific community was seriously contemplating the idea that we had come across technology from another civilization. The burden of proof was immense, but the potential discovery warranted the most rigorous investigation humanity could undertake. The line between proof and pareidolia remained sharp. But with each new analysis, each independent confirmation, and each failed attempt to explain away the anomalies, the balance was gradually tilting towards a conclusion that would alter everything we thought we knew about our place in the universe. Part 10. The message unfolds. Content, form, and meaning. What 3i Atlas was attempting to communicate became evident only after months of meticulous analysis, and the message was both more intricate and more functional than anyone had anticipated. The communication was not a salutation or a philosophical discourse, it was a set of instructions. Dr. Yuki Tanaka at the Tokyo Institute of Technology spearheaded the international decryption effort. Her expertise in information theory and signal processing made her exceptionally suited to unravel the layered complexity of the visitors' broadcasts. What at first seemed to be simple sequences of prime numbers were revealed to be headers for more elaborate data packets, each one expanding on the mathematical principles established in the preceding transmissions. The initial layer served as a mathematical groundwork, setting up shared concepts that would permit more advanced communication. Prime numbers led to algebraic expressions, which then progressed to geometric theorems. The visitor was instructing us in its mathematical language before trying to transmit more complex information. The second layer introduced fundamental physical constants: the fine structure constant, Planck's constant, the speed of light. But these were not merely confirmations of universal truths. They were presented with a level of precision that surpassed humanity's current measurement capabilities, indicating that our visitors had a more accurate grasp of fundamental physics. The third layer was where the message took a fascinating turn. The visitor started to transmit what could only be interpreted as technical specifications, detailed blueprints for building a radio beacon with capabilities far exceeding current human technology. The designs were remarkably considerate of human constraints. Instead of presuming boundless resources or advanced materials, the design utilized technologies that a 21st century Earth could plausibly create. The beacon would necessitate a vast array of precisely synchronized transmitters, but the individual parts were within the scope of human engineering. Even more notably, the design incorporated optimizations for Earth-specific rotational period and magnetic field. This was not a standard template, it was tailored to our planet, implying that the visitors had studied Earth's characteristics in depth before initiating contact. The fourth layer held what Dr. Sarah Kim at MIT termed the network map, a description of how the proposed beacon would connect to what seemed to be a galaxy-spanning communication network. The map depicted relay stations situated at strategic points throughout our local cosmic neighborhood, each identified by exact astronomical coordinates. Some of these locations matched known stars, while others indicated empty areas of space where gravitational lensing might concentrate and boost signals over interstellar distances. The visitor was outlining a communication system that used the galaxy's own structure as its infrastructure. The ethical considerations woven throughout the technical documents showed a sophisticated understanding of biological worlds. The message featured symbols and concepts that clearly related to living systems, planetary ecosystems, and what could only be understood as principles of conservation. There were underlying warnings about keeping electromagnetic silence near biological surfaces, and suggestions that powerful transmitters should be located far from inhabited planets. The encoding method itself was a marvel of information theory. Every data packet contained multiple levels of error correction, guaranteeing that the message could be retrieved even if significant parts were corrupted or lost. A temporal framework allowed the transmission to be pieced together correctly despite interruptions, Doppler shifts, and the sporadic visibility of the moving transmitter. Clear markers indicated byte order, units of measurement, and coordinate systems, thus preventing the kinds of confusion that can occur when species with different mathematical backgrounds try to communicate. The message was engineered to be decoded by any intelligence capable of detecting it, irrespective of their specific technological journey. Yet the most curious part was what the message did not include. There were no personal messages, no cultural items, no attempts at casual conversation or philosophical discussion. The visitor's message was purely practical, a technical guide for joining what appeared to be an established interstellar communication network. The implications were immense. Humanity was not just getting its first message from another civilization. We were being invited to become part of a community of intelligences that has been active across the galaxy for an unknown length of time. Public involvement in the decryption process had been priceless. Citizen science platforms enabled thousands of volunteers to assist with various parts of the analysis. Pattern recognition challenges were assigned to students in classrooms around the world. This joint effort marked the largest coordinated intellectual undertaking in human history. Convergent translations started to appear as different teams, working separately, arrived at similar understandings of key sections of the message. This overlap provided assurance that the decryption was on the right track despite the unprecedented nature of the communication. The Deep Space Optical Communications demonstration on the Psyche mission had offered crucial insights into high-bandwidth optical communication over interplanetary distances. These lessons guided speculation on how the visitor might broaden the conversation from simple radio signals to more advanced data exchange. But perhaps the most crucial element of the message was its implied deadline. The technical plans for the beacon specified temporal coordinates, exact timing instructions for its activation, and synchronization with the larger network. If humanity wished to join the galactic community, we had a finite period in which to construct and activate our station. The moment of decision was drawing near. The visitor had given us detailed instructions for building our own interstellar communication system. The technology was demanding, but not impossible. The question was whether humanity was prepared to declare its existence to whatever civilizations might be listening across the galaxy. Constructing the beacon would be an irreversible act. Once switched on, Earth's involvement in the galactic network would be permanent and observable by any intelligence monitoring the communication channels. We would cease to be an isolated planet yelling into the void. We would become a part of something immense, ancient, and utterly beyond our present comprehension. The choice, in the end, was straightforward. Stay isolated or join the dialogue that has been occurring among the stars since before human civilization even began. Part 11. Second-order effects, technology, law, and power. The moment humanity seriously contemplated constructing an interstellar beacon, everything shifted, not just our technology, but also our politics, our economies, and our very definition of what it means to be human. Engineering teams across the globe initiated rapid development of the technologies outlined in 3i Atlas's message. The beacon's requirements stretched the limits of human manufacturing, but they did not exceed them. Ultra-thin metamaterials, meticulously engineered at the nanoscale, would serve as the primary transmitting components. low-noise oscillators synchronized with atomic frequency standards would furnish the stable time references essential for galaxy-wide communication. The most formidable challenge was synchronization. The beacon was designed to be a network of thousands of individual transmitters spread over hundreds of kilometers, all functioning in perfect unison. The necessary timing accuracy on the nanosecond scale and maintained over interplanetary distances necessitated breakthroughs in both quantum timekeeping and distributed control systems. Cooperative radar-laser hybrid systems became a vital technology. By merging radio broadcasts with precisely timed optical pulses, the beacon could meet the bandwidth and power demands specified in the visitor's instructions. This dual-mode design also offered redundancy. If one system were to fail, the other could sustain communication. Yet, every advance in beacon technology had dual-use potential. The same precise timing systems required for interstellar communication could also guide intercontinental ballistic missiles with unparalleled accuracy. The high-power transmitter arrays could potentially disrupt satellites or even be used as directed energy weapons. Advocates for planetary defense called for transparency protocols that would permit international oversight of the beacon's construction and operation. The technology was simply too potent to be developed in secrecy. Any nation or entity building interstellar communication systems would have to agree to inspections and verification measures. Legal systems found it difficult to keep pace with technological advancements. The Outer Space Treaty of 1967 regulated activities in space but was silent on the matter of communicating with alien civilizations. The Liability Convention of 1972 dealt with damages from space objects but could not foresee conflicts over interstellar messaging privileges. Model laws started to be proposed by legal experts worldwide. Contact governance treaties, suggested for adoption by the United Nations, would create international standards for extraterrestrial communication. These frameworks drew heavily on existing arms control and environmental protection treaties, but were adapted for the distinct challenges of interstellar diplomacy. The question of who represents Earth ceased to be merely philosophical. With the visitors' beacon plans in hand, various nations and organizations began to assert their right to build and manage humanity's connection to the galactic network. NASA suggested an international consortium, much like the International Space Station Partnership. China declared its intention to build its own independent beacon system. Private corporations presented their own proposals, contending that commercial rivalry would speed up development. Data rights became a central point of contention. Would the beacon's transmissions be public knowledge, accessible to all of humanity? Or would the nations and organizations responsible for building the system regulate access to interstellar communication? The precedent set by Earth's first beacon would likely shape communication governance for future generations. The economic repercussions were felt in every industry. The rare earth elements needed for the beacon's construction caused commodity price surges that lasted for months. Lithium, already vital for battery technology, gained even greater strategic importance as engineers understood its role in quantum frequency standards. But the most significant economic transformation was psychological. Investment timelines stretched from quarters and years to decades and centuries. Companies started to plan for market opportunities that might not arise until their great-grandchildren were at the helm of business. The cosmic viewpoint fundamentally changed how humans perceived time and value. Cryptocurrency markets gave rise to hundreds of galactic coins intended for interstellar trade. Most were blatant frauds, but some were earnest attempts to devise communication protocols that could function across species. The mathematical complexities of achieving galaxy-wide consensus pushed blockchain technology in new and unforeseen directions. Religious and philosophical institutions grappled with humanity's altered status. Were we still created in God's image if we shared the galaxy with other intelligent beings? Did our moral duties extend to civilizations we had never encountered but might soon join? Theological seminaries began to offer courses in astroethics and interspecies communication. Educational systems saw an unprecedented surge in demand for programs in physics, mathematics, and engineering. Students who had previously shown no interest in technical fields suddenly wanted to grasp the science behind interstellar communication. Community colleges started to provide beacon literacy courses, teaching the fundamental concepts required to take part in humanity's cosmic dialogue. Environmental factors added complexity to the beacon planning. The transmitter arrays would consume vast amounts of electrical power, potentially gigawatts during peak usage. Carbon-conscious power sources became crucial to avoid aggravating Earth's climate issues while aspiring to the stars. Solar farms and fusion reactors gained new investment as the environmental movement joined forces with space communication advocates. Ground-based transmission systems brought up concerns about the electromagnetic effects on wildlife. Birds, whales, and other creatures that use Earth's magnetic field for navigation could be disturbed by powerful radio signals. Careful site selection and transmission protocols would be necessary to reduce the ecological footprint. The cislunar region emerged as humanity's newest frontier for beacon development. The Moon's far side provided natural shielding from Earth's radio interference, making it a perfect spot for sensitive receiving equipment. Near-Earth asteroids could offer the raw materials for construction without the environmental impact of mining on Earth. Space traffic management systems, already under pressure from growing commercial activities, faced new difficulties from beacon-related infrastructure. Orbital debris from construction could endanger existing satellites. Communication interference between beacon systems and traditional spacecraft necessitated meticulous frequency coordination. International cooperation became both a necessity and an opportunity. No single nation had all the resources needed for rapid beacon construction. Successful projects depended on sharing technology, funding, and expertise across traditional political divides. The beacon acted as a catalyst for the kind of global collaboration that had been hard to achieve for purely Earth-based problems. But cooperation also came with risks. Shared beacon systems would require governance structures that could withstand political shifts and international disputes. What would happen if participating nations had disagreements about message content or transmission priorities? How would humanity settle conflicts when the outcomes could affect our standing in a galactic community? The institutional frameworks created for beacon governance would likely influence humanity's approach to space development for centuries to come. The precedents established, transparency versus secrecy, competition versus cooperation, national interests versus species interests, would shape everything from asteroid mining to interstellar exploration. As construction timelines shortened and launch dates drew near, humanity found itself transforming not just its technology, but its very identity. We were no longer an isolated species shouting into the void. We were getting ready to become citizens of a galaxy-spanning civilization whose true extent we were only just starting to comprehend. The implications reached far beyond the beacon itself. Every facet of human society, from education and economics to governance and philosophy, was adapting to the reality that we shared the universe with intelligences whose abilities might far surpass our own. The secondary effects of contact were reshaping civilization itself. Part 12, After the Echo, Who We Choose to Be. 2 years following the initial radio exchange with 3i Atlas, humanity was at a juncture that would shape our species for ages to come. The visitor had left our solar system in early 2027, accelerating on its hyperbolic path towards an unknown destination. But its message lingered, stored in our databases and our collective consciousness, a guide for joining a galactic community we had never known existed. The choice before us was deceptively straightforward: build the beacon or stay silent. Yet the consequences of each option touched every part of human civilization. Three main scenarios were at the forefront of policy discussions in the world's capitals and academic circles. The conservative approach recommended maintaining listening stations and broadening our passive SETI efforts, but refraining from any active transmissions that could draw unwanted attention. Supporters of this view contended that we needed decades or even centuries to better comprehend the galactic community before announcing our existence. It was better to observe discreetly, learning about our potential neighbors before disclosing our location and abilities. This strategy had clear benefits. It was safe, reversible, and permitted humanity to progress at its own pace. We could continue to advance our technology, spread throughout the solar system, and establish the economic and social groundwork necessary to interact with more advanced civilizations as equals, not as dependents. However, critics highlighted the disadvantages of isolation. The beacon designs provided by 3i Atlas showcased technology centuries beyond human development. A refusal to engage could indefinitely slow our progress, leaving us permanently trailing behind civilizations that have been communicating for millennia. The participatory approach suggested constructing a modest, carefully managed beacon system that could be turned on or off based on humanity's collective decision. This middle path would demonstrate our ability to join the galactic network without an immediate commitment to active involvement. The technical challenges were considerable, but not insurmountable. A distributed network of transmitters synchronized by quantum timing systems placed in space to prevent interference with Earth's biosphere. The beacon would initially operate at very low power, announcing our presence without overwhelming nearby communication nodes with novice broadcasts. Governance structures would be established to ensure that no single nation or entity had sole control over humanity's voice in galactic matters. The content of messages would necessitate international consent through enhanced UN frameworks. Transmission schedules would strike a balance between scientific discovery and diplomatic prudence. The ambitious approach advocated for a full commitment to interstellar communication within a decade. Proponents argued that the visitors' beacon plans included time-sensitive coordination instructions. If humanity wanted to join the galactic network effectively, we had to act swiftly while the visitor's message was still current and applicable. This path held the promise of rapid technological growth and immediate access to whatever knowledge the galactic community was prepared to share. Early involvement in interstellar communication could provide humanity with scientific and technological breakthroughs that might solve our most critical issues: climate change, resource scarcity, and the difficulties of expanding beyond Earth. But the risks were immense. Full participation in galactic communication would make Earth permanently visible to any intelligence monitoring the network. We would be bound by relationships and duties we could not fully grasp. Withdrawing from the network after joining might prove to be impossible or come with dire consequences. The discussion went beyond conventional political divides. Progressive environmentalists found common ground with conservative military strategists in supporting the cautious strategy. Libertarian technologists joined forces with international diplomats in favor of a measured approach. The cosmic viewpoint had disrupted traditional political alignments. Public opinion was split but actively involved. Surveys consistently indicated that a majority supported some form of beacon construction, but with significant differences depending on the specific proposals and timelines. The most favored approach blended elements of all three scenarios, building beacon capability rapidly, but activating it slowly with extensive safeguards and international supervision. The Galileo project, initially created to look for evidence of extraterrestrial technology, transformed into a permanent program for technosignature detection and analysis. Its expanded purpose included watching for more interstellar visitors, analyzing the beacon plans from 3i Atlas, and laying the scientific groundwork for future contact situations. Funding came from unexpected places. Tech billionaires who had previously concentrated on Earth orbit projects redirected their investments towards interstellar communication. Nations that had never been part of space programs began to contribute to beacon development consortia. The decentralized nature of the required technology enabled smaller countries to make significant contributions through specialized manufacturing or research. Legal frameworks continued to be developed through international talks. The Outer Space Treaty's prohibitions on national claims to celestial bodies were broadened to include interstellar communication nodes. New protocols were established for sharing alien technology and distributing any benefits gained from galactic participation. The issue of institutional oversight became paramount. Beacon systems designed to function for centuries needed governance structures that could withstand political shifts, economic crises, and social changes. The precedent of ensuring continuity across generations would decide if humanity could be a dependable member of any galactic community. Scientific preparations moved forward irrespective of policy choices. Radio telescopes kept watch for additional visitors and tried to detect the wider galactic communication network described in 3 Atlas's message. Gravitational lensing experiments were conducted to see if stellar focal lines could indeed boost signals over interstellar distances, as the visitors' specifications hinted. Prototype beacon parts were tested in Earth orbit and at the lunar Lagrange points. The technical difficulties were being overcome by human ingenuity, but the engineering schedule was still daunting. Full beacon capability would demand at least a decade of dedicated development, likely more. Psychological support networks were established to assist individuals and communities in adjusting to the cosmic perspective. Contact counseling became a recognized field, helping people come to terms with the knowledge that humanity was part of a larger galactic civilization. Support groups formed spontaneously, uniting people who were grappling with finding meaning and purpose in a suddenly immense universe. Educational curricula were updated to ready students for a future that might involve regular interstellar communication. Children who would come of age in the 2030s and 2040s started to learn mathematics and physics with the clear understanding that they might use these skills to communicate with alien intelligences. The generational gap was stark. Older adults often had difficulty with the implications of contact, while younger people adapted readily to the idea of galactic citizenship. Children seemed almost unfazed by the news that other intelligences existed, as if they had always known and were just waiting for the adults to realize it. As the decade unfolded, humanity's choice centered on a fundamental question of identity. Were we explorers or protectors? Did we define ourselves by our readiness to venture into the unknown, or by our dedication to safeguarding what we had already built? The answer, when it arrived, embodied both tendencies. Humanity would construct the beacon, but with great care. We would join the galactic community, but on conditions that maintained our independence and safeguarded our home planet. The compromise pleased neither the most daring nor the most cautious, but it represented a species-wide agreement on who we aspired to be. The night sky appeared different now. The specks of light that had once seemed remote and inert were now seen as potential homes for intelligences whose messages might already be journeying towards Earth at the speed of light. The cosmos had transformed into a neighborhood, vast beyond belief, but no longer devoid of life. In the end, this was perhaps 3i Atlas's most profound gift, not the technology to join a galactic civilization, but the awareness that we had never been alone. Somewhere among the stars, other minds were posing the same questions, confronting the same difficulties, and reaching for the same distant lights that had fueled human dreams since we first looked up in awe. The conversation that started with humanity's unintentional radio signals and was continued by 3i Atlas's meticulously designed reply was far from finished. It was, in truth, only just starting. The real question was not whether we would join the galactic community, but what kind of neighbors we would decide to be. As Earth's first interstellar beacon powered up for its initial test transmission, a soft carrier tone ascended through the prime number frequencies, our species' first deliberate words in a dialogue that had been awaiting us since long before we learned to speak.